called the Smart Factory IoT Monitoring System. This is a complete end-to-end industrial IoT solution built on Arduino Uno microcontroller simulated using PiximLab and connected to the ThingsBoard cloud for real-time monitoring and control. The idea behind this project is simple. In modern factory, you cannot afford to have blind spots. You need to know what's happening on your production floor and in your warehouse at all time. If your machine overheats, if humidity spikes, if someone enters restricted areas after hours, you need to know instantly and react automatically. That's exactly what this system does. It has two sensor nodes deployed at two critical factory locations. Node 1 is on the production line and Node 2 is in the warehouse. Both nodes collect real-time data, send it to the cloud every 5 seconds, and give operators a live dashboard to monitor, control, and respond from anywhere. The entire system was simulated in PiximLab, which means every sensor, every relay, every LED behaves exactly as it would on real hardware without needing a physical setup. This makes it ideal for rapid prototyping and demonstration. Slide 3. System architecture. Now let's look at how system is structured. We follow a classic 3 IoT architectures. Tier 1. The perception tier is where data is born. The two PiximLab Arduino nodes simulated the physical factory environment. Virtual sensors generate temperature, humidity, vibration, motion, light, and door signals. The firmware on each node reads these signals, processes them into engineering units, and prepares them for transmission. Tier 2, the transport tier. It is a MQTT. MQTT stands for Message Queuing Telemetry Transport. It is the industry standard protocol for IoT communication. It's lightweight, runs over TCP, and is designed for constrained devices with limited memory and bandwidth. Our nodes connected to ThingsBoard built-in MQTT broker on port 1883. Each device authenticates using a unique access token, so there is no risk of one device data mixing with another. One is Tier 3, the application tier, is ThingsBoard Cloud. When a telemetry message arrives, ThingsBoard stores the value, evaluates rules chain conditions, and update all dashboard widgets in real time without the browser needing to reload. If an alarm condition is triggered, it appears in the alarm table immediately. Operators can also send command back to down the system using RPC, which ThingsBoard routes to the correct device. The data flow is clean and unidirectional for telemetry. Nodes push data up, commands flow down via the RPC topic. This separation makes the system predictable and easy to debug. Next one is hardware design. Even though hardware is simulated in PiximLab, every component is mapped exactly as it would be in real deployment. Let me walk you through both nodes. Coming to node 1, production line, pin D2 connected to the DHT22 sensor. This gives us air temperature and humidity. The DH222 has plus or minus 0.5 degrees Celsius accuracy and plus or minus 2% RH accuracy, which is more than sufficient for factory floor monitoring. And pin A1 connects to the LM35 analog temperature sensor. The LM35 outputs 10 millivolts per degree Celsius. And pin A0 connects to the potentiometer that simulates a vibration sensor. We take 4 consecutive ADC samples and average them. This reduces noise and gives a stable reading between 0 and 1023. And pin D3 is a push button with input pull up. When the button is pressed, it goes low, which is interpreted as the machine being on. This is active low logic, which is more noise resistant than active high. Pin D4 drives the relay. This relay controls whether production equipment is energized or de-energized. It can be triggered automatically or via a remote RPC command. Pins D5, D6 and D7 drives 3 LEDs. Green for normal operation, yellow for warning or sensor error, and red for critical faults or disconnections. And pin D10 to D13 are reserved for virtual Ethernet interface via SPI. These are used by PiximLabs network stack and must not be used for anything else. Coming to node 2 warehouse, the DH2 on D2 works the same way, but here the humidity reading has an extra role. It triggers the auto ventilation logic. A0 connects to an LDR. Low ADC values means low light. When the reading drops below 300, we set is dark flag to true, which can trigger lighting alerts. D3 connects to the DT D3 connects to a PIR HCSR 501 motion sensor. When it detects movement, it goes high. We implement a 10-second hold timer so the motion detected flag stays true for at least 10 seconds after the last detection. I will explain why this matter in the future slide. D7 connects to a read switch on the warehouse door. With input pull up, a low reading means the door is open. This is used for security monitoring after hours. D4 drives the ventilation relay. This is the key actuator for node 2 activating the warehouse fan when humidity gets too high. Next slide is software architecture. We followed a strict modular architecture with 6 clearly separated modules, each with a single responsibility. Config.h is a single source of truth for the entire system. All pin numbers, IP addresses, MAC addresses, MQTT broker addresses, access tokens, and threshold values like humidity critical levels are defined here as a constants. And the code is the sensor manager that reads all sensors, and actuator managers controls the relay and LEDs, and a network manager that handles MQTT connections and auto reconnects, a telemetry manager that builds and sends JSON data to the cloud, and RPC handler that receives remote commands. This modular design makes the code easy to maintain and scale. Next one is telemetry keys. Every piece of data the system collects has a specific telemetry keys that gets published to ThingsBoard. Let me go through them. Node 1 publishes 8 keys. Temperature. 8 temperature from the DHT22 rounded to 1 decimal place. And humidity. Relative humidity in percent also from the DHT22 with same error catching behavior. LM35 temperature, machine surface temperature from the LM35 analog sensor. This is a critical for detecting overheating machinery before it causes damage. Vibration, the 4 sample average ADC reading from A0. The dashboard shows this is a time series chart with threshold line at 700. Values above this are considered high vibration. Machine status, a boolean. One means the machine is on, derived from the button state on D3. Relay state, a boolean showing whether the production relay is currently energized. This reflects the actual physical state regardless of whether it was triggered by RPC or by logic. And sensor error, a boolean that goes to 1 when the DHT22 fails to respond. This is the system ways of telling the operator that sensor data may be stale. Uptime, seconds since the last boot, derived from millis, useful for detecting unexpected restarts. And coming to node to warehouse, publishes 9 keys, all of the above equivalent plus LDR value. The raw averaged ADC reading from the LDR, useful for calibration and trend analysis, is dark, a derived boolean when LDR drops below 300. Is dark becomes true, this can trigger lighting alerts or automated responses. Motion detected. One when the PIR has a fixed within the last 10 seconds. The whole timer ensures we never miss a detection even if the PIR pulses briefly. Door open. 1. When the read switch reads low, meaning the door is physically open. These keys appears on the ThingsBoard latest telemetry tab within the seconds of the node booting up, confirming the connection is healthy. Next one is key features and logic. Let me highlight the smart logic we built in first. First one is the auto ventilation. When warehouse humidity crosses 85%, the relay activates automatically without any human input. Second one is PIR hold timer. Motion stays flagged for 10 seconds after last detection, preventing false off readings. Third one is sensor error catching. If the DHT22 fails, the last valid reading is used so we don't trigger false alarms. And fourth is MQTT, auto reconnect. If the network drops, the node reconnects on its own within 30 seconds. And LED status skip. Green is equal to connected and normal. Yellow is a warning or sensor error blink. It will blink. And red is the critical threshold or disconnected. Identical schemes on both nodes for operator consistency. And last one is the RPC commands. Set relay. Both nodes set LED node 1 and individual D5, D6, D7. Get status returns relay state uptime and freeze SRAM, all routed via V1 revise me RPC topics. Next one is the dashboard and UI design. We built 3 dashboards on ThingsBoard. The factory overview gives operators a single screen to monitor both nodes at once with temperature trends chart and alarm table. The Node 1 detailed dashboard has gases, a vibration chart, LED indicators, and a remote relay switch. And coming to Node 2 dashboard shows humidity trends, motion and door indicators, and a ventilation override switch. All gases use green, yellow, and red zones, matching the physical LED stays on the device. Next one is alarm rule engine. Dashboard shows what's happening. The rule engine acts on what's happening automatically without waiting for a human to notice. Our alarm threshold table covers every critical parameter. 8 temperature above 30 degrees Celsius triggers a warning. Above 35 degrees Celsius triggers a critical alarm with a red LED. Warehouse humidity above 70% is a warning, above 85% is a trigger both critical alarm and auto ventilation relay. Vibration above ADC 700 is monitored on the chart but does not trigger any alarm. It's an operator review metric. LDR below 300 sets the is dark flag and lights the yellow LED. Machine temperature from the LM35 above 30 degrees Celsius is a dark, above 40 degrees Celsius is a critical alert, shown on the dashboard GURS. And QTT disconnects lights the red LED after 5 seconds and must reconnect within 30. DHT22 failure blinks the yellow LED and sets sensor error. The temperature rule chain is the most important rule we configured. It's called factory temperature monitor and is assigned to the default device profile, meaning it applies to both nodes automatically. The flow has 5 steps. First, every incoming telemetry message enters the rule chain. Second, it goes through a message type switch to confirm it's a telemetry message. Third, a JavaScript filter evaluates whether message temperature is greater than 35. If true, it routes to alarm creation. If false, it routes to alarm clearing. Fourth, if the temperature is above 35, ThingsBoard creates high temperature alarm with critical severity. This appears instantly in the alarm table on every dashboard. And fifth, this is an important detail. When the temperature drops back below 35, the rule chain automatically clears the alarm. Operators don't need to manually acknowledge and close it. The system resolves. Next one is testing and acceptance criteria. No system is completely without rigorous testing. We defined and executed 10 test cases, 6 hardware tests, and 4 software integration tests. On the hardware side, we verified that both nodes display the correct IP addresses in the PiximLab serial monitor on boot. We adjusted the DHT22 slider in PiximLab and confirmed the dashboard curves updated live to match. We toggled the PIR sensor and confirmed that motion detected held at 1 for the full 10 seconds hold period. We toggled the read switch and confirmed door open appeared on the dashboard within one published cycle, that is less than 6 seconds. We reduced the LDR value below 300 and confirmed is dark activated correctly. And coming to on the software integration side, we disconnected the Ethernet during operation and confirmed the red LED activated and the node reconnected automatically within 30 seconds. We simulated a DHT22 failure and confirmed a sensor error went to 1. The yellow LED blinked and the last valid temperature and humidity values continued to be published. No crash, no false alarms. We pub- we pushed humidity above 85% and confirmed the ventilation relay activated without any RPC command, fully automatic. We then sent a set relay false RPC command while auto ventilation was active and confirmed relay deactivated within 6 seconds. RPC override worked correctly. Finally, we raised the temperature above 35 degrees Celsius and confirmed high temperature critical alarm appeared in the Thingsboard alarm table and then confirmed it cleared automatically when the temperature dropped. All acceptance criteria were met. Telemetry appears within 10 seconds of power on, dashboard updates within 6 seconds of any sensor change, auto ventilation triggers within 6 seconds of humidity reaching 85%, RPC commands execute within 6 seconds, critical alarms raise within 10 seconds of the with 10 seconds of the threshold being breached, and both nodes recover MQTT connectivity automatically without human intervention. And last one, project delivered. What project delivered here is, let me bring this all together. What we have built is fully functional. End-to-end industrial IoT monitored and control system. Two Arduino based sensor nodes simulated with perfectly fidelity in PiximLab continuously monitor critical factory parameters and publish 8 to 9 telemetry keys every 5 seconds to Thingsboard Cloud over MQTT. And the system is not just monitoring tool, it is an intelligent automation system. It detects when warehouse humidity is too high and activates ventilation on its own. It handles sensor failures gracefully without generating false alarms. It gives operators complete remote control over relays and LEDs from a browser. It raises a clears and alarms automatically based on configurable thresholds. The architecture is production ready. The code is modular and maintainable. The dashboards are clear and operator friendly. The rule engine is extensible. Adding a new alarm type is a matter of adding one rule chain node. Adding a new factory node requires only creating a new Thingsboard device and uploading the firmware. The dashboard structure supports it without redesign. Every single acceptance criteria refined at the start of this project has been met and verified through structured testing. This project demonstrates that with the right tools and architecture, a small team can build a robust, scalable, real world IoT solutions rapidly and cost effectively. Thank you very much. Next one is project overview. Node 1, the production line, is responsible for monitoring the health of your production environment. It reads air temperature and humidity using a DHT22 sensor. It reads machine surface temperature using an LM35 analog sensor. This is important because a machine running too hot is a safety and quality risk. It also reads vibration levels using an analog potentiometer connected to the ADC, which simulates a vibration sensor, and it detects whether the machine is on or off using push button with active low logic. It also controls a relay that can shut down equipment remotely if needed. And coming to node 2, the warehouse node has a different focus. Warehouse need environment control. It monitors temperature and humidity and critically. If humidity crosses 85%, it automatically activates ventilation relay to protect stored goods. It also monitors light levels using an LDR sensor and raises is dark flag when warehouse needs lighting. PIR sensor detects motion, useful for security after hours. And read switch on the door tells operators whether the warehouse door is open or closed at any moment. And coming to things about cloud is the brain of the system. It acts as the MQTT broker, receiving all telemetry from both nodes. It stores data, runs rule chains to detect alarm conditions, display beautiful live dashboards, and sends remote commands back to the device via RPC. No local service is needed. It runs entirely on cloud.thingsboard.io accessible from any browser anywhere.